Are you ready to let go of everything you thought you knew about the concept of time? To put it succinctly, there is no such thing as time. And it's not just us saying that, but the results of a new research study. But what is meant by this radical assumption? Why could what we commonly understand as time actually be nothing more than an illusion of quantum physics? And what conclusions can be drawn from this revolutionary assumption? Albert Einstein once said, "For us physicists, the distinction between past, present, and future is nothing but an illusion, albeit a stubborn one. Subjective time, with its insistence on the now, has no objective meaning." And indeed, the more we study this topic, the clearer it becomes that what seems so banal to us in our everyday lives could not be more mysterious. Because while time often represents only a few numbers on the clock or a specific day in the calendar for us, we usually completely ignore the question of what time actually is. By definition, however, we are dealing here with a physical quantity that describes the sequence of events in a unique, irreversible direction. And that literally affects everything. Because the universe also moves not only spatially, but also temporally, in detail, from its beginning, the Big Bang, to its end. Consequently, time is strictly linear, and yet it continues to present us with new puzzles to this day. As mentioned at the beginning, a new study has now come to the conclusion that time is not a fundamental pillar of the universe at all, but merely an illusion that results solely from quantum entanglement. But what is meant by that? Does this mean that there is no such thing as a beginning and an end to our current video? Well, unfortunately, it's not quite that simple. To understand why time has become the focus of countless scientific discussions to this day, we should first consider the different paths available to experts in this regard. On the one hand, there is Einsteinian physics, which explains the processes of the universe on a large scale. On the other hand, there is quantum mechanics, which consequently deals with what happens on a small scale and often seems to contradict classical physics. Let us just think of Schrödinger's cat, which forms the core of a thought experiment published by the eponymous physicist Erwin Schrödinger in 1935. In this context, a cat is locked in a box together with a deadly poison capsule, but no one knows when the poison will escape. As a result, the cat can be considered both dead and alive at the same time. Its state would only change to one of the two states through direct observation. But what does a cat in a box have to do with quantum mechanics? Well, it's quite simple. Quantum mechanics also recognizes a superposition of this kind. That is, the superimposition of different states. Only when a measurement or observation is carried out does the corresponding system assume one of the superimposed states. In detail, Schrödinger's aim at the time was to show the incompatibility of the quantum mechanical and classical physical principles, because a cat cannot be dead and alive at the same time. The wondrous world of quantum entanglement. However, quantum physics not only recognizes superposition, it also recognizes quantum entanglement. In principle, particles in normal quantum theory do not have a unique state. You can only assign them relative probabilities for being in one state or another. As already mentioned, this only changes in the course of a measurement, when the particle assumes one of these states according to these probabilities. However, it becomes even stranger when two particles interact with each other, because then they can be entangled. In other words, their individual probabilities are no longer independent of each other, but coupled to each other. They are now components of a complicated probability function that describes both particles equally. To understand this better, let's look at the following example. In an experiment on entanglement, two electrons are generated simultaneously, and their spin, or in other words, their intrinsic angular momentum, is measured in two different devices. Ultimately, it turns out that the electrons each have opposite spin, which is all the more surprising given that, according to the superposition, their state was not yet determined at all before the measurement. The bottom line is that it was only the measurement that caused one particle to decide on one state and the other particle to decide on the other at the same time. Despite their spatial distance from each other, the two electrons are therefore to be understood as a coherent system. However, quantum entanglement also violates the assumption of locality, which states that processes only have an immediate effect on their direct spatial environment. In the case of quantum entanglement, the entangled particles can be light years apart and still be inseparably linked. What's more, the spatially separated particles exchange their information instantaneously, or in other words, without any time delay. In view of this, it's hardly surprising that Albert Einstein had his problems with the so-called spooky action at a distance. After all, the transfer of information would have to take place at speeds faster than light. And although the principle of quantum entanglement sometimes seems very confusing, it may now offer researchers the opportunity to finally uncover the true nature of time. Is time just an illusion? Published in the journal Physical Review A, the lead authors of the study from the Italian National Research Council point out that it is possible to reconcile time with both the classical laws of physics and the rules of quantum mechanics, if it is a manifestation of entanglement. But first things first, in quantum mechanics, time embodies a fixed phenomena, an inexorable flow from the past into the present. However, time remains outside of the bizarre and ever-changing quantum systems and can only be recognized by observing changes in external units, such as the hands of a clock. According to Einstein's general theory of relativity, however, time is interwoven with space and can even be distorted and stretched in the process. As a result of this contrast between classical and quantum mechanical laws, scientists were at an impasse for a long time. But the aforementioned study now suggests that time may only be an illusion resulting from quantum entanglement anyway. But what is meant by that? Well, in fact, the time problem is not new in the world of quantum mechanics. The Page-Wouters mechanism, proposed as early as 1983, is a theory that states that time for an object only arises through quantum entanglement with another object that acts as a clock. For a non-entangled system, however, there is no time at all, and the system perceives the universe as frozen and unchanging. By applying this mechanism to two theoretical quantum states, a vibrating oscillator and a group of tiny magnets acting as a clock, the researchers observed that their system could be described by the Schrödinger equation, which predicts the behavior of quantum objects. However, this happened without the explicit use of time. The role of the clock was taken over by the states of the tiny magnets. In the next step, the experts repeated their calculations twice more, first assuming that the magnetic clock and then the oscillator embody macroscopic, or in other words, larger objects. Their equations simplified to those of classical physics, indicating that the flow of time is a consequence of entanglement, even for objects on a large scale. In this context, the experts emphasized that the correct, and above all, logical direction for them is to start from quantum physics and understand how to get from it to classical physics and not the other way around. Other experts, however, have been rather cautious in their statements. Although it is mathematically consistent to imagine universal time as entanglement between quantum fields and quantum states of 3D space, no one knows whether this image will give rise to something new or fruitful, such as modifications to quantum physics and the general theory of relativity. What Michio Kaku says about time. But suppose we have really been misunderstanding time the whole time. Wouldn't it also be conceivable that one day we might uncover characteristics that currently seem absolutely unimaginable? Well, that's exactly what Michio Kaku was asked during an interview. More specifically, the world-famous physicist was asked to share his thoughts on the concept of time and time travel. And he had truly amazing things to tell. But just listen for yourself. A quote. Let's start with Isaac Newton. Newton believed that time is like an arrow. Once shot, the arrow moves in a straight line. 1 second on Earth is the same as 1 second on Mars, 1 second on Jupiter, and so on. The arrow never changes direction. But then along came Einstein. He said, not so fast. Time is like a river that winds, speeds up, and slows down. The question that concerns us so much is this. Can the flow of time possibly split? Can it form different river arms, or is it possible for it to form loops and meander around itself? In this case, time travel is something we have to take very seriously because Einstein's equations allow travel through time, and the concepts for time travel are actually compatible with Einstein's theories. For example, gigantic rotating cylinders. You move around the cylinder and come back before you left. Time and space are like a kind of rubber, like a trampoline net. If we stretch the trampoline net too much, it can tear. And maybe we can shape the trampoline into a pretzel, which would allow us to travel back in time. But unfortunately, as always, there is a catch. The energy required to do this is gigantic. Not even a nuclear bomb has enough energy to operate a time machine. For a time machine, we would need the energy of an exploding star. As is well known, the theoretical question of time travel is accompanied by some paradoxes. For example, what would happen if we killed our grandfather in the past and thus deprived ourselves of our own existence? Well, according to Michio Kaku, there are two ways to resolve these nagging thought games. The first way is called self-consistency. Even if we point a loaded gun at our grandfather, something would prevent us from pulling the trigger. It would simply not be possible for us. And further, maybe there is some hidden physical law that prevents us from creating time paradoxes, but I don't think so. I think that the flow of time splits in such cases, exactly as we see it in Back to the Future. That the simplest way to explain time paradoxes, because we don't have to add any further assumptions except those of quantum mechanics. If we go back in time and save Abraham Lincoln from the assassination attempt, then we would have saved a different Abraham Lincoln. If you shoot your own parents before you are born, then you have shot someone else's parents. So, if you will, we change a parallel past that we ourselves create. Even Stephen Hawking said that there must be some physical law that prevents us from traveling back in time. And we have looked for it, but found nothing. We know of no laws of physics that prevent us from traveling backwards through time. It seems to be compatible with the laws we know. The thing is, we need the energy of the magnitude of a star to do that. The civilization that realizes this must be very advanced, but it is not excluded. And of course, we don't want to exclude you from our upcoming videos. Press the thumbs up and subscribe now to stay up to date from now on. We'll see you soon.